once again, everyone. Thanks for checking back again and again. Boy, this could be my longest video ever. I don't even know if it'll fit on YouTube, but if it doesn't, it'll be on Canvas. Stoichiometry, moles, grams, volumes, aqueous. Oh yeah, that means in water, right? So, big part of chemistry is done in water because I suppose so many things dissolve in water and it allows the ions or species to mingle intimately and come in contact with each other. And it's a good way to pour things and store things. So there's a crucial definition, very, very important. If you haven't heard of it before, it's pretty simple actually, but very, very important. It's called molarity. It's how we describe how much stuff's in the water, how many moles of solute, moles of things that we're interested in reacting, in what total volume. The more moles in more moles per liter, we say the more concentrated. The fewer moles per liter, we say it's more diluted or watered down. In shorthand writing, we say molarity, capital M, moles of solute, liters of solution, or number of moles in volume. Or also simply we say molarity, moles per liter, or moles per volume. So how many moles are dissolved in how many liters of total liquid? Yeah, it's not necessarily liters of water. It could be liters of something. Well, aqueous means water, but if there's a whole bunch of moles and they take up some space as well, and your volume of water may not be the total volume. But in any case, we'll worry about that next semester actually, chapter 11. So memorize this, that molarity is moles per liter, or if you switch it around, moles can be determined by taking the molarity, molar concentration times the volume. So you should know this. This is just as important as changing grams to moles and moles to grams. Believe it or not. I have the possibilities go on and on. Some examples. 3 moles of NaOH per liter of solution, 3 molar NaOH. 4 moles of H2SO4 sulfuric acid per 5 liters of solution. Divide the two numbers, 0.8 molar sulfuric acid. Yeah. Alright. 0.07, so the numbers get messy. You see, you just divide the numbers. But if you know the moles of solute in liters of solution, you do the division. These numbers are all small, but still comes out to 1.9 molar hydrochloric acid. You'll notice I tried to take the time to write aqueous in back of all these things. So 43 grams of salt in 2.1 liters of solution. But you know what? It's not grams, it's moles. So I went ahead and in the numerator just changed grams to moles. Sodium plus chlorine weighs 58.5 or 58.45 at least grams per mole. And so I do this division, 43 divided by 58.5, and then also divide by 2.1. So you see in the upstairs, I might just change grams to moles in one fell swoop and then write divided by the total volume. Alright, sometimes it can get messy. 1 copper plus 1 sulfur plus 4 oxygens plus 5 waters adds up to 249.7, almost 250 grams per mole. 3 sig figs is 250. So 73.4 divided by, yeah, and then the volume. Alright, yeah. And the examples go on and on. But going the other way, if I knew the molarity and the volume, I can multiply them. And that's, usually it's sorted in a sentence, something like 2 liters of a 1.7 molar KOH solution. And the word of in most story problems means times, and indeed it means times here as well. So molarity times volume gives you moles. Moles of solute in the solution. And so whenever I see of, liters of, molar, molarity times liters gives you moles. And this would be 0.0177 moles of lithium ion and also 0.0177 moles of nitrate ion. So there's a whole bunch of ions floating around in the water as those ionic species bust up. Yeah, and it's also possible, you realize, once you take molarity times volume to get the moles of solute, that you can change moles of solute to grams of solute, just like we've always been doing. But that multiplication there, that's kind of the new idea. And of course that would be, oh yeah, shut up, okay? Potassium permanganate, a famous oxidizing agent. Sometimes I won't change from milliliters to liters. Sometimes I'll leave it as milliliters, gives me millimoles. That sounds kind of weird to get a millimole, but if I'm doing a comparison to something else or a titration, that's often very easy. I mean, very simple. If I'm not converting moles to grams or anything, you could leave it in millimoles, see what happens. You can't lose it altogether if you keep track of it and know later that you need to change to grams instead of getting milligrams, and just go ahead and change it to moles. But so become comfortable with milli versus mole, milliliter, liter, millimole, mole. The milli is the small unit, right? Milliliters times molarity, millimoles of phosphoric acid. Did it again. Cobalt chloride, 45 milliliters of 0.559 molar cobalt chloride gives me millimoles of cobalt chloride. Here I changed from millimoles to moles to convert moles to grams. But if you didn't, if you just 25.2 millimoles times 129.8, that would give you what? 3,270 milligrams of cobalt chloride. Oh yeah, so usually in a titration, it's best to consider the molecular equation, a balanced this reacts with this kind of a thing. And I'm not going to introduce net ionic equations right now, but I will later. So if I had 1 mole of acid reacting with 1 mole of base, it's a 1-to-1 ratio, which is pretty nice. That means 1 mole of this reacts with 1 mole of this. If I then knew that 37 milliliters of 1.8 molar HCl reacted with 0.75 molar base, but didn't know this volume, it's real simple. It's 1 mole of this equals reacts with 1 mole of this. So whatever the moles are here needs to be equal to the moles here. So I write an equal sign in between. The moles here equal the moles here. Moles of acid, moles of base if it's 1-to-1 ratio. If it's a 1-to-1 ratio. And I get 66.6 millimoles of acid must equal 66.6 millimoles of base, but I just don't know this one yet. So this one times this one divided by this one gives you this one. That's a valuable concept. Another way to write it would be to say this one times this one equals this one times, this is a more long-winded version, but since 1 mole of this reacts with 1 mole of this, I could use a conversion factor and say convert millimoles of acid to millimoles of base. Then, via the definition of molarity, which was 0.75 moles per liter, I use this as a conversion factor. It's kind of upside down, but I wanted the moles of NaOH to cancel with the moles of NaOH here, convert to liters. And voila, it works out to the same answer. There's another more dangerous way to put it. And I say it's dangerous because it's only useful if you're very, very careful in what scenario you use it. That is to say, the moles of reactant 1 will equal the moles of reactant 2 or 3 as long as it's a 1-to-1 ratio. Only if it's a 1-to-1 ratio. M1V1 equals M2V2. And that looks like I had this up here. Oops, right here. Yeah, in that very same form. Molarity times volume equals molarity times volume. And that seems to simplify everything to put it in that context, but it only works if it's 1-to-1. And I'll say that again and again and again and again and again. Other ways to say molarity of acid, volume of acid, molarity of base, volume of base. A is for acid, B is for base. Moles of acid equal moles of base. But again, it doesn't have to be acid-base titration. It could be anything that's 1-to-1. Also, it's called the dilution equation. If I had a concentrated liquid, lots of solute, and I want to water it down, I go M concentrated volume concentrated equals molarity of the diluted times the volume of diluted. But you see all over here, I put only for 1-to-1. Does this work? Alright, so if that's true, for example, what if I had baking soda and vinegar? Here's my baking soda aqueous. This is kind of weird. Usually we just pour liquid aqueous vinegar onto solid baking soda, but I can dissolve baking soda in water. So here's some baking soda in water. 1.1 moles of this baking soda per liter. So if I have 73 milliliters of that, and I have a concentration of vinegar 0.87 molar, what's the volume of this vinegar that I should use? Well, it's just this one times this one divided by this one. 99, almost 100 milliliters. That's just too simple. Doesn't get any simpler than that. Here's another one that's is 1-to-1. One of these react with one of these to give 2 waters actually and 1 barium sulfate. But since it's a 1-to-1, one of these react with one of these, I can know the molarity molar concentration and volume of my base and not my molarity of my acid. And this is usually the way it's done with the titration. To take a certain amount of this, react a known concentration of base with it, and stop at the endpoint where usually an indicator changes color. And anyway, this one times this one divided by this one. Oh, you'll notice here I didn't change this from milliliter. This milliliter matches with this milliliter, and they actually cancel. So in a sense, yeah, I don't have to worry about the liter thing. That's why sometimes you don't have to convert from milliliters to liters if you're careful with your units. In the language of dilution, we could say, if I took 12 molar hydrochloric acid, 50 milliliters of it, and watered it down to 250, so there's my 50 milliliters of 12 molar, water it down to 250, what's the new concentration, the molarity of the diluted? Well, you see the answer. It's just this one times this one divided by this one, 2.4 molar. That makes sense because 12 molar watered down might give you 2.4 molar. Or the reverse question, what volume of concentrated 8 molar should be diluted to 2 liters to make a 0.37 molar ammonia solution? These questions are always weird. You have to read them like 3 times to figure out what the world they're asking. But one thing that helps is if you have the word of in between a molarity and a liters, which you often will. But I determined that this volume with this molarity, this volume, this molarity, and question, how much of the concentrated stuff should I take? So I take 92.5 milliliters and water it down to 2 liters of that concentrated stuff, water down to 2 liters to make the more concentrated, less concentrated 0.37 molar. Very, very helpful in the lab. What happens when the reactants are not 1-to-1? Well, you got to look at it more carefully. Like here's one that's 3-to-1. Let's just take it slowly then. If it's 3-to-1, I'll take molarity times volume like I always do. So 57.2 milliliters of 0.913 molar KOH, and that gives me 52.2 millimoles of KOH. But now it's a 3-to-1, so you know what? Let me take that 52.2 millimoles of KOH and do a conversion factor, a mole ratio. The reactants were 3 of these to 1 of these. So 3 of these to 1 of those. And lo and behold, it's less. Well, duh, it's 3 times less. Then I can take that 17.4 millimoles and just use my milliliters. And I had 25 milliliters of this stuff. So the millimoles over the milliliters, the millis cancel, and moles over liter is the definition of molarity. This is just crazy once you get the hang of it, but it's going to take a while. Here's the 2-to-3 ratio. This is a solid, but I can still use my aqueous stoichiometry skills on this acid. So I took 300 milliliters times 1.75 molar sulfuric acid gives me 525 millimoles of the acid. So how much of this is that going to work with? I don't know. I do know. It's right here. Let's do the millimole. Oh, I did convert from millimoles to moles. If I didn't get rid of the milli here, guess what? That would just continue on down to here, and this would be 120,000 milligrams. Yeah. But anyways, you see where the 3-to-2 ratio comes from? 3 of these acids with 2 of those aluminum hydroxides. And then I converted moles of aluminum hydroxide to grams of aluminum hydroxide. And that would be a solid. That doesn't happen to dissolve in water very well. That's why I had to go with a solid. Here's another weird stoichiometry one. It's a 4-to-3 ratio. Ammonium phosphate and lead nitrate react to give 12 moles of ammonia. Holy cow, 12 moles of ammonium nitrate. And 1 mole of lead 4 phosphate. Is that right? Yeah, lead 4 phosphate. Anyway, if I knew a molarity and volume for one of them, multiply it out. But then what's this volume of this one over here? It's not a 1-to-1 ratio, so that's ugly. But not too bad. I'll take that 26.22-ish millimoles and convert it from moles of ammonium phosphate to moles of lead nitrate. It's a 4-to-3 ratio. So 26.2 times 3 divided by 4 gives me my millimoles of this one. Then if I know the millimoles of the unknown volume, I can pretty much find the volume. Moles equals volume over volume times molarity, or switch those around a little bit. Volume is moles divided by molarity. So moles divided by molarity, this is millimoles by molarity, gives me milliliters. Or if you don't like that, you take the original 19.66 or 19.7 and use the molarity as a conversion factor. The moles, this mole cancels this mole, leaves me with milliliters. That's interesting. Or not. Hi, chihuahua. This goes on forever, doesn't it? It does, but I got to stop soon. I'm almost, how many more slides do I have? A couple more slides, 2 more slides. Also nice to be able to do this. How would you make an ion? Describe the ionic molar concentrations resulting from 5.73 grams of magnesium bromide dissolved into 400 milliliters of solution. Well, I can't work with grams, so I changed grams to moles. This, you know where this comes from. Add up 1 magnesium and 2 bromines. So this one divided by this one, it's in a 400 milliliter or 0.4 liter solution, and there's my molarity. So you know what? That means square brackets mean molar concentration, molar aqueous concentration usually, not always, but it's 0.0778 molar magnesium bromide. Well, you know what? 1 magnesium 2 plus ion comes from 1 magnesium bromide unit, so it's the same number for the concentration of magnesium ion, but it's actually twice that number for the bromide, because 2 bromide ions were for every 1 magnesium bromide unit, so the concentration of bromine is more than that. Or if I said what's the total ion concentration, I would take this one plus this one, since it's in the same volume. You can add them straight away, and the molar concentration of ions, 0.233 molar, that's 0.233 moles of ions per liter of solution. One more. This is a mouthful, isn't it? Let's think about a sugar-water solution. Sugar is pretty heavy. It's a big molecule, 342 grams per mole. How would I make 750 milliliters of a 1.43 molar sugar-water solution? Well, as soon as I see molarity and volume, I can multiply that out. 0.75 liters. I went ahead and decided to change to liters here instead of milliliters because I wanted to work in grams instead of milligrams. And gives me 1.07 moles of sugar. So what is 1.07 moles of sugar? It comes out to 367 grams of sugar. So how would you do it? Take 367 grams of sugar, dissolve it in a little bit of water, enough water so that it will dissolve, mix it up good, and then top it off to 750 in maybe a volumetric flask that has a special line painted or scratched on the neck to come to 750, and then you shake it up good and make sure it's all dissolved, mixed well. Whew, I don't know if any of that makes sense, but it's a good place to start, and we'll practice with it. See you in class, guys. Thank you all.